Okay, now it's time for another AP Physics 2 Cram video. These will be on magnetism, and again, like all my Cram videos, just kind of talking about concepts. Might be a little rougher than usual than my other movies, but let's go ahead and get started here. So we have a positive charged particle in the presence of a magnetic field, and the magnetic field is showing X's, so that means it's going into the page. So it's our job then to figure out the value of the magnetic force acting on this. Well, the equation force magnetic is going to equal the magnitude of the charge multiplied by magnetic field multiplied by velocity times the sine of theta. Now in this case we're perpendicular, so the sine of theta of 90 is going to be 1. So we just have QBV. So what's going to happen here? Well, I'm going to place my fingers in the direction, okay, for my right hand roll in the direction of velocity. I'm going to curl them inwards, and I'm going to notice that I curl my fingers inward towards the page, towards the magnetic field direction. I will notice then a magnetic force going in this direction. And I have a magnetic force that's perpendicular to the motion of the particle. So this particle indeed will do a circle. Try to draw a pretty nice circle there, because anytime you have force perpendicular to the velocity vector, you will have a circular motion happening. That's centripetal acceleration going on. So that's if we are perpendicular to the field. Now what if we're not perpendicular to the field? Well, we have a velocity vector here and a magnitude and direction of a magnetic field there. So I'm going to break my velocity vector up, okay, in terms of x's and y. So I'll go ahead and do that right here. I'll go ahead and finish up there. So this is going to then be velocity x, and this will be velocity y. So what I noticed, well, velocity y is going to be parallel to the magnetic field, so there's no magnetic force acting on that. Now what about velocity x? So I'm going to point my fingers in the direction of velocity. Okay, now I got to curl my fingers upwards to the top of the page, and my thumb is going to show a magnetic force that's coming out of the page, and I'll try to draw that for you. And of course that'll be perpendicular, so I'm going to try to draw that coming out of the page. Sort of did that. Okay, so that's going to cause the particle is going to be moving like this. Okay, we're then going to be doing a circle coming out of the page at you. Okay, but we still have a velocity vector going upwards. So we're going to see a spiral. I wish I could draw circles more symmetrical there. So we'll see it spiraling upwards, okay, in the direction of the velocity vector. But again, we'll be coming out of the page this way, back into the page, out of the page, back into the page as we spiral upwards. So the easiest way I find is to, since we're not perpendicular to the magnetic field, is break the velocity vector up into Vx and then Vy. So let's go ahead and talk more about this. Now what about magnetic fields created by current carrying wires? Well, this will be the second right hand rule. I'm going to point my thumb in the direction, okay, of the current. And then my fingers are going to wrap concentric circles such that I will have x's here, because the concentric circles are going to be going into the page here, like that. And then I'll do dashed lines. It's going to be coming out of the page over here, so I'll see dots like this. So we have indeed a magnetic field, okay, that is generated, okay, by a wire. This also gets confused with the magnetic force acting on a wire. So what's the difference between those? Well, let's pretend I'm drawing a wire here and the current's going in this direction. Okay, and I have a magnetic field going into the page. Now this magnetic field is caused by some other magnetic field. Maybe an electromagnet or just regular bar magnets. So I is going in this direction here. So let me do right hand roll. So stick our fingers in the direction of current. We're going to wrap our fingers into the board, and we'll have a magnetic force then acting in this direction here, perpendicular to the wire. So let's label that as magnetic force. So what's the difference between these two examples? Well, this wire is generating magnetic field, concentric circles. This current in this wire is exposed to some exterior or external magnetic field, and that would cause a magnetic force going upwards. So this one I call the thumb right-hand rule, and this one I guess I call the normal right-hand rule. And that's really the difference between those. Okay? So this one, force magnetic, equals B I L, and then there should be a sine theta after that. See if I can fit that in there, sine theta. Or perpendicular again, so the sine of theta, 90 is going to be 1 there. Now what about this? Well, this will have an equation where magnetic field is generated by the wire. So B is mu naught. Okay, permittivity of free space, mu naught, equals 4 pi times 10 to the minus 7. So that's mu naught I being the current, divided by 2 pi r. And r, of course, is the distance we are from the wire. So the farther I get away from the wire, the magnetic field generated by the wire, okay, does decrease. And it decreases by radius on the bottom. All right, now what if we have, two wires that are right next to each other? Well, we can draw our little X's and circles here. So this wire here, point my thumb in the direction of current, we're going to have X's here because of that one. And of course we'll have dots over here, because we'll have concentric circles of magnetic field. Now let me do a red color for this wire here. For this wire here, again, will be the same pattern, except we'll have dots caused by this one and X's over here. So what do we derive here? Well, we can derive an equation. Again, force magnetic on a wire, okay, does equal BIL, and of course times sine theta. Now, assuming these two wires are in the same plane to each other, we would then have a magnetic field on this wire. There are X's going into the board because of this wire, and it's perpendicular, because as the circles go around like this, when they hit the page here, they will be perpendicular. And this wire over here has red dots acting on it, so in other words, the magnetic field is coming out of the page for that. Okay, and it's because of the presence of this wire. So in doing this, to solve this equation, we actually really like the force magnetic per unit length. That, of course, is going to equal the B, which is going to come from our above equation, 4 pi times 10 to the minus 7, which is mu naught, multiplied by I. And if you want to call, let's say we're trying to solve the magnetic force per unit length on this wire here. Okay, then we would have I2 times I1, because the I1 is for the magnetic field, and then we'll divide that by 2 pi r. We take the L and divide it into the other side. So this right here, 4 pi times 10 to the minus 7 times I1, is the magnetic field caused by this wire, and then of course including the divided by 2 pi r. And then the I2 is for the I in our BIL equation, and then I took L to the other side. So the force magnetic per unit length would have this equation. Now what about the direction? Well, this wire here is being exposed to X's, or into the page magnetic field, because of the presence of this wire. So I place my fingers in the direction of the current here. I'll wrap them into the board. We'll see that there's a magnetic force pointing upward this way. Okay, and because of Newton's third law, or we can just look at this one here, we will also have a magnetic force pointing this way. Okay, and that's because the current's going through here. We have to take our right hand and flip it, point our fingers upwards, because this one's experiencing red dots. In other words, magnetic field coming out of the cage because of the presence of this wire here. And the magnetic force would be pointing downwards. So these two wires will be attracted to each other because the currents are going in the same direction. Well, that's all for video 1. I will have, for video 1 for magnetism, I'll have the second one ready soon.